today's lecture, I will introduce vector functions or functions of vectors. Okay. In that, I will talk about two types of functions, what are called as scalar and vector fields, and then we will briefly mention vector differentiation. Okay. But the more details of vector differentiation I will talk in the next class, where we will talk about gradient, divergence and curl. Okay. So, let us start with functions. Okay. Here we will restrict the discussion to 2-dimensional and 3-dimensional vector space. Okay. So, in if you have a 3-dimensional vector space, then this any vector can be written R as in terms of 3 coordinates x, y, z. Okay. So, R is a vector in this vector space. These are the components of R x, y, z. Okay. So, this is just like a point in 3D Cartesian coordinate system. If you have a 2-dimensional vector space, okay, then you have a 2-dimensional space, and you can think of an arbitrary vector R as having 2 components, the x and y components, or you can also think of it in the xy plane in Cartesian coordinates, and you can think of a vector as some arbitrary point in Cartesian coordinates. So just to illustrate, if you have 2-dimensional space, you have x, you have y, and suppose you take an arbitrary point, you can think of this as this vector R. Okay, so and these are the x and y coordinates, x coordinate, and this is the y coordinate. Okay. So you can think of a vector as a point in this 2-dimensional coordinates, and therefore I can represent it as R, which has 2 components x and y, and in 3D space R has 3 components x, y, z. So a function of a vector, okay, you can think of it as a function of multiple variables. So a function of a vector means it is a function of R, okay, and R contains x, y, z. R is x, y, z. The information that x, y, z together give is exactly that information of R. So instead of thinking of f of R, I can think of f of x, y, z, or in 2 dimensions I can think of f of x, y. So a function of a vector can be just thought of as a function of multiple variables. Okay. So for example, if you can think of any function of multiple variables, for example f of r, this is example, f of r equal to, let us say 3x plus 2y z. Okay. It can be any function. Okay. You can multiply, you can take squares, you can do anything you want, or you can take f of x. I can write it as f of x, y, z is equal to 4x cube y plus 3 y square. Okay. Now in this case, an arbitrary function of x, y, z, in this particular case it has no dependence on z, but even that is a general function of x, y, z. You can also have a function of x, y, z that has no y dependence, or you can have a function that has no x, y, z dependence. You can have, so for example, even f of x, y, z, if I equal to 3, this is also a function of x, y, z. Okay. So these three are examples of functions of vector. Okay. So you can do this in many different ways, and the point is, whenever you have a function of many variables, you can think of it as a function of a vector. Okay. So now there are 2 kinds of functions. Okay. So these functions of multiple variables, you can think of them as vectors. They are also referred to as fields. Okay. And there are 2 kinds of fields. One is called a scalar field, and the other is called a vector field. Okay. So in a scalar field, your function that you have is basically a scalar. That means you give x, y, z, you give it into the function, and what you get is a real number. Real number if it is a real function, if it is a complex function, you will get a complex number. Okay. But essentially you get a scalar, real number, or a scalar. Okay. So this is called a scalar field. Okay. And the examples that we talked about here are all examples of scalar fields. Okay. So, so scalar fields, in scalar fields you have the function which is just a scalar. Okay. That means given x y z, it returns a real number or a scalar. In vector fields, the function that you get for any x y z, you get a function which itself is a vector. So, f itself is a vector. So, f has 3 components. So, it has the x component, which is again a function of x y z. It has the y component, which is also a function of x y z, and it has a z component, which is also a function of x y z. Okay. So, equivalently I can write this as f x, f y, f z, and I keep in mind that each of the components themselves are functions of x y z. So, for example, I can have an example where this vector field equal to 3 x y I plus 4 z square j plus 3 x z minus 2 sin z times k. So, this is my f x, this is my f y, and this is the f z. Okay. So, what we did here is we said that if these f x, f y, f z are all functions, are all scalar fields. So actually f x itself is a scalar field, f y itself is a scalar field, f z itself is a scalar field. So f x, f y, f z are scalar fields, and these are components of the vector field f. Okay. So these are 2 ways you can define functions of vectors. Okay. And now we have these scalars and vector fields, and what are the examples, where do you see these? So, the most common example of scalar and vector fields which you will encounter is in potential theory. So, the potential energy okay, at a point in space, at a point in 3D space. Okay. So, this is written as V of x, y, z. So, it is a function of x, y, z. Okay. So, suppose you take any point in space, you ask what is the potential energy, that is written as V of x, y, z. Okay. So, this is an example of a scalar field. Because the potential energy is a scalar. Okay. Now, this potential energy actually it might lead to something like a force at any point. So, if you put a test charge at any point, it might experience a force because of this potential energy, and so you can ask what is the force at any point x, y, z. This is a vector field. So, this is one example of scalar and vector fields. Okay. You can have many such examples. Now, one very common example that you learn in statistical mechanics is you might consider a box. You might consider a system where you have lot of particles. Let us say it might be a fluid system, or it might be a system of gases. So, you have lot of particles, okay, and the density is not same everywhere. So, the density rho is a function of x, y, z. So, this is an example of a scalar field. Okay. So, the density is an example of a scalar field. Okay. Now if you have a fluid, then the particles at each point might move with different speeds. Okay. So, the velocity, this is velocity field. This is very commonly encountered in fluids, and this is an example of vector field. So I just wanted to show you some examples of scalar and vector fields that you will encounter in various courses. One is the scalar field, and one is the potential energy, which is a scalar field, potential energy, or just the electrical potential. Okay. Then you could have a force at any point. Okay. So that could be a vector field. Similarly, you could have if you have a fluid, then you can think of the density of the fluid at any point as a scalar field. You can think of the velocity at any point in the fluid, okay, as a vector field. Okay. So these are some examples of scalar and vector fields. Of course, there are many more examples, okay, but I just wanted to say where you encounter these kind of objects. In fact, as we said, any function of multiple variables you can think of as a scalar field. Okay. So you might plot, you might be calculating the density of particles, okay, like for example, you have a wave function psi of r, okay, and from this you calculate the probability at r as psi star r, psi of r. Okay. Now these are all this is a scalar field, okay, because you can calculate the probability of finding a particle at some point in space. Okay. So that is another example of scalar fields. Okay. So I mean, you encounter these objects all the time in various courses. Okay. So you should be aware of what scalar and vector fields are. Okay. Now so what we have done here is we have tried to define functions of vectors. Okay. So we have tried to take vectors and we have tried to define functions of vectors. Okay. And in defining these, we came as there can be two types of functions. Functions which are scalars, which are called scalar fields, and functions which are vectors, which are called vector fields. Okay. So scalar functions are called scalar fields, vector functions are called vector fields. Okay. Now there is another common terminology that is used when you are dealing with vectors, and this is the idea of vector operators. Okay. So an operator is some object. Okay. So it is denoted by O hat. So operator is denoted by O hat. Okay. Now the operator has to operate on something. So it acts on a vector. So it might act on a vector A to give you another vector. So it might give you some vector and I will just call it B. So a typical operator acts on one vector and gives you another vector. Okay. Now A and B of course belong to the same vector space. Okay. So you can have an operator that acts on a vector space to give you acts on a vector in a vector space to give you another vector in the same vector space. Okay. So now these vector operators can do various things. I mean, you can think of this as taking the vector and transforming it to another vector. Okay. Now you can think of this as a vector field. You can you can think of B as a function of A. Okay. But there are certain kinds of operators that we will be really interested in, and these are what are called as linear operators. Okay. So let us take an example. Let us take some examples of operators. So you could have an operator that takes and let us work in 3D. So in 3-dimensional space, I can have an operator as this operator I defined as add a constant vector C0. Okay. So that is my operator. So what does it do? So suppose I take operator acting on A. I have to what the operator does is it adds a constant vector C0. So I get A plus C0. Now A plus C0 is also a vector. Okay. So A plus C0 is also a vector in the same vector space. So that is how this operator works. okay, and I will just for convenience I will call this O1. Okay. You could have many different kinds of operators. You could have operator O2. Okay. So, multiply A by a scalar C. Okay. So, then or multiply, I should not say multiply A, multiply whatever the vector is by a scalar C. Okay. So, for example, if you have O operator acting on A, you will get C times A. Okay. So, this is another operator, okay, or let us be precise and call it O2. Okay. So, what you saw is you saw an operator that adds a constant vector C0. Okay. This is an operator that multiplies it by a constant C. Okay. And just to inform you, this is a translation, okay, and this is a stretch. Okay. So what do you mean by translation and stretch? Okay. So what I want to say is that if you had a vector A, okay, and let's say I will just take for convenience this as my C0. Okay. So, then when I add C0 to A, what I will get is I will get a vector like this. Okay. So this is my B vector, okay, which is A plus C0. Okay. So what it did is it took this vector and it moved this point up by it moved this point in the direction of C0. Suppose I had some other vector A, suppose I had some other vector here, it would do the same thing, it would again move it up, move it in this direction by this point. So, the new vector will be this. So what the operator does, so if I take this as A prime, then this is operator O1 operating on A prime. Okay. So that is why this is a translation operator where it just shifts or it just translates the vector by a certain amount. Okay. Now, the other operation we said is called a stretch, okay, where what it does is it takes the vector and multiplies it by a scalar. So, you get a vector in the same direction, and based on C it will be either be longer or it will be shorter. So the stretch operator, okay, I will show this in blue. So, what it does is it takes A and it multiplies by C. So this is my C times A. Okay, if C is less than 1, then this length will be shorter. If C is greater than 1, it will be longer. Similarly, it will take this and it will shrink it by the same factor. So, whatever the factor was here, okay, the same factor C times A prime. Okay, so these are common operators. Okay. Now, you can have other operators. You can as you can see, you can imagine an operator that does something called a rotation. So, it can take a vector, rotate it by some angle. So you can have I will just write it here, rotation operators. I will come back to linear operators in a few minutes, okay. But you can have an operator that does a rotation. So what it does, so I will just show this in green, okay. So it takes A and it rotates by some angle theta. So let us just call this R, rotate by theta, rotate let us say about some axis, rotate let us say around z axis by theta. So this is a rotate about z axis by theta. So this is an example of a rotation operator, and you can see what it will do is if this is my x and y plane, it will take this vector A and it will give you this green vector which is r by this angle theta. So, r z of theta operated on A. Okay. So, it will take any vector, similarly it will take this vector A prime and it will give you, it will rotate this by theta and it will give you something else, it might give you something like this. So, this is r z of theta into A prime. Okay. So, essentially this is another example where it takes a vector and gives you another vector. Okay. So, now we will come to a certain class of operators which are called linear operators. Okay. So, let us just come to the class of operators called linear operators. So, what is a linear operator? So, a linear operator, you can think of it this way. So, suppose you have an operator O, okay, it acts on A, on C times A plus B. So, operator should act on any vector, it can act on any vector, it should act on all the vectors in the vector space. Okay. So, C times A plus B is another vector in the vector space. Okay. So, if it operates on this, if I can write this as C times operator on A plus operator on B. Okay. So, then this is called a linear operator. So, a linear operator is an operator which when it acts on a linear combination of vectors, okay, gives a linear combination of operator acting on each of the vectors. Okay. So, now linear operators are actually extremely common in very important in quantum mechanics. In fact, a large part of the formulation of quantum mechanics is based on linear operators. Okay. But there is something else about linear operators. Okay. What linear operators can do is they can only there are only certain kinds of transformations on certain kinds of operators which are linear. So, for example, you can have an operator. So, this is example of linear operators. Okay. So, last time we said you know add a constant vector. C0. So, that is an example of a linear operator and you can verify that it is trivially linear. Then multiply by a scalar C. So, that is also a linear operator. Okay. Then we talked about rotations, rotation about some axis. Okay. So, that is also an example of a linear operator. Okay. What is an example of an operator that is not linear? Okay. So, an operator that is not linear okay. So, suppose I define my operator as something that take dot product of vector with itself and multiply by vector, by same vector. Okay. So, what this does is it takes O and when it acts on a certain vector A, what it does is it takes A dot A. Okay. So, you take the dot product and so A dot A is a scalar. So, it takes this and multiplies it to A. So, now you get a vector. Okay. Now, you can show that if you do this, then you can show that this is not a linear operator, okay, because I mean it's fairly easy to show that it does not satisfy the condition for a linear operator, and you can trivially show. Suppose I just take CA, suppose I take O of CA, okay. So this is clearly a constant times A, okay. So this is not equal to C times O of A, okay. This is actually C cube times O of A, right. So it is C cube times A dot A into A, okay. So this is C cube times O of A, okay. So clearly it is not C times O of A, okay. So it is not a linear operator, okay. Now linear operators have something very they have a connection with matrices, okay, and you can see this in the following way. See, suppose I take my vector, okay. So let's consider 3D space again, okay. So my vector V has components Vy, Vz, okay. Now I can think of my operator, okay. I will write this as a column vector. So Vx, Vy, Vz, and I have my operator here. So here I have my operator, okay, and that gives me some other vector, some new vector. I'll just call it Vx prime, Vy prime, Vz prime, okay. So this operator acts on V to give you V prime. So I'll just define V prime equal to Vx prime, Vy prime, Vz prime, such that operator acting on V equal to V prime, okay. So once you write it in this form, okay, you can ask what is a linear operator. So you can have I mean there is no relation between V and V prime, okay. You can operate by any operator and you can get another vector, okay. Now linear operators are those where O can be written as a matrix, a 3 by 3 matrix, okay. So for linear operators you can generally write this operator O as a 3 by 3 matrix, okay. And so an arbitrary linear operator in 3D space can be written as a 3 by 3 matrix, okay. And you can easily show that if you write it as if you write this operator as a 3 by 3 matrix, then this condition will hold, the condition for a linear operator will hold, okay. So we will keep in mind that a linear operator can be written as a matrix, and or you can think vice versa, matrix can be thought of as a linear operator on a vector, okay. You can think of it as a linear operation on a vector, okay. So in the next class what I want to talk about is vector differentiation, where since you can define a function of a vector, you can also think of derivatives with respect to that function. So today we talked about scalar fields and vector fields. We talked about functions of vectors. Now you can ask, what about derivatives with respect to these vectors, derivative with respect to vectors, and that will be the topic of the next class, which will be vector differentiation, where we will talk about gradient, divergence and curl, okay. So I will stop for today now. Thank you.